this. Sometimes I go down to the bottom of the pool, and if I let the air out of my lungs, I can actually lie on the bottom of the pool. Tell the lifeguard you're going to do that, though. They really don't like you lying on the bottom of the pool. That's what they're looking for, and they'll be like, ah, right? Tell them, hey, I'm going to lie on the bottom of the pool. I know what I'm doing, right? I can do that. I don't float. They tell you you float, but I don't. If I let the air out of my lungs, I can actually sink to the bottom and look up. And then I like to blow little bubble rings. You can make rings of bubbles. Try it. It's really fun. You just kind of go and blow, and you can make like a ring that goes up and it goes, it's kind of cool, right? But when you look up, what do you see? Isn't the bottom of the water at some distance like a mirror? And you see the bottom of the pool? Try that. This is your homework, okay? Yeah, lie on the bottom of a pool, look up, and at some point you're seeing a reflection. The light's trying to leave at some point at an angle called the critical angle, right? So I'll draw another guy here, right? Hence my joke about let's subject this to critical thought. But you didn't get that joke because you didn't know it was a critical angle, right? Okay, at some angle here, this angle here is 90 degrees, okay? Theta R is 90 degrees, right? This angle here is the critical angle, and therein lies the rub. If you want to find, say it again? That's the refracted angle. If the refracted angle is 90 degrees, what happens is the light is totally reflected off the inside of the slower medium. Totally reflected off the inside of the slower medium, and so it really doesn't go along the surface. What it really does is it just bounces, or if you're retracing it, right, when you look there, you're actually seeing the side of the pool, a reflection. It looks like a mirror, doesn't it? Have you seen this? Try it sometime. It's maybe something you've never done, right? What's really cool is to get into a pool that doesn't have any ripples on it yet. My mom has a swimming pool up at 1 Jefferson Parkway. They've got this pool that everybody shares. I often get there and there are no ripples. Get into the water without making very many ripples, like don't do the cannonball, right? Slide down there, lie on the bottom of the pool, and look up. And when you look up at that critical angle, we'll figure out what it is for water, okay? At that critical angle, everything else, when you look up, you see a distorted image of the pool surround, the whole interior, right? And then as you look at that critical angle, you see this roughly circular point where you're suddenly seeing the bottom of the pool. It all looks like tile or something like that, right? It's a very cool thing. Now to calculate a critical angle, what you do, let me redraw this so it's not quite so confusing. The critical angle, if this is the boundary, here is slow. The critical angle happens in the slow medium. You can always go from fast to slow. At any grazing angle, if I come in here, it'll always bend into the medium, right? It's going from slow to fast that it can't do, right? So if we get something that is at the critical angle, if this is the critical angle, all you do is you make this angle of refraction 90 degrees, right? Okay, so theta 2, if theta 1 is the critical angle, theta 2 is 90 degrees, right? No new formula needed, just an understanding, right? And so now we can use our IB formula, or as I much prefer, Snell's law, n1 sine theta 1 equals n2 sine theta 2, right? So the critical angle formula is n1 sine theta critical equals n2 sine of 90 degrees. What's the sine of 90 degrees? It's 1, right? Okay. So now we can plug this in. Let's make this be air, 1.00. Let's make this be water, 1.33. Right? So the angle that you would look at, we can just plug this in, 1.33 sine of the critical angle equals 1.00, and then times the sine of 90, which is 1, right? So now how do you solve for the critical angle? Isn't it just the inverse sine? Critical angle is the inverse sine of 1 over 1.33. Yeah, and this 1 is the ratio of the indices of refraction. Yeah, if one of them is 1 and the other is something bigger, which it would kind of have to be, right? Okay, then it's 1 over that something. I'll give you this clue. Let's say somebody goes swimming with their diamond ring. Diamond is 2.42, water is 1.33. Where does the 1.33 go there? Where does the critical angle occur of a water-diamond interface? Does it occur in the diamond or the water? Which can what light not get out of, the diamond or the water?
Diamond.
The diamond, because it can't get out of the slower medium into the faster. In this case, water is the faster, correct? Yeah? So a diamond would have the critical angle. Now, which one would be where in this formula? Yeah, the 2.42 would be on the bottom, 1.33 would be on the top. What if you tried to do the other one? Does there exist an inverse sine of 2.42 over 1.33?
No.
No, if you can't calculate it, you cannot calculate an incorrect critical angle. You can get a domain error, but you cannot get it wrong. This is what I'm trying to say.
You can never get this wrong.
You can never get it wrong. You can just get a domain error and be stupid and go, oh, there isn't the one. No, right? But there it is, right? Okay, so what is this angle? Let's go inverse sine of 1 divided by 1.33. 48.8 degrees, right? Yeah? That's kind of cool. So have you ever wondered how fiber optics work? I don't know if you've thought about this, right? But a fiber optic is a long pipe through which light travels. It's a long pipe through which light travels, and the notion is that you've got this thing, and it can go around little corners and stuff like that, right? Okay. Well, here's the idea: is that a laser beam traveling down this pipe still goes in a straight line, right? But when it hits the inside of the pipe, it strikes it at a subcritical angle. Yeah. And it is always total. This is called total internal reflection. As it strikes the edge, it always strikes it. It's the glancing blows that reflect, correct? Yeah? Kind of like bullets. Bullets work this way too, right? Okay. A glancing blow will reflect, right? And if it's a glancing enough blow, that is, the pipe is narrow enough, then the light will stay inside the pipe. That's kind of cool, isn't it? Do I have one of those? Why, yes, I do. Okay. And now the laser is on the tripod, right? Ordinarily, to take the laser off the tripod would be a very laborious task involving the unscrewing of a screw. But this one has a quick release! All for $19. Fred Meyers. There we go. What was I going to do? Oh, I was going to demonstrate something. Here we go. I got so excited about the quick release that I forgot my demonstration. Here we have it. Laser light. Somebody turn off the light. I'm going to send the laser lights down this windy path. Ouch. Nobody got the joke. Did you get it?
Yeah, I got it.
Yeah, okay, thanks. Nobody got the joke? Ouch.
I don't get it.
E.T.? Yeah, E.T. Here we go. 2 people got the joke. All right, yeah, I don't know. Notice that it does not look like a laser beam anymore. I'm guessing that bouncing off of scratched, the surface of scratched acrylic or polyethylene or whatever this is, right, okay, has made it like kind of diffused. But there it is. It's largely inside the pipe. It is reflected like that. That's kind of fun. Say it again? Oh, it's escaping out the front. See my finger?
Oh, okay.
Yeah. It's coming in. Yeah. Right, so when it hits that front surface, it's hitting that at a supercritical angle, right? It's hitting it at above the critical angle, and it can escape out the front. But as it bounces many, many times going through here, it's always hitting it at a subcritical angle, right? Or what is it? I don't know. But it's bouncing, yeah? It's a glancing blow. Okay. Say it again?
Is it possible to cause it to hit the critical angle?
Well, it'd be very hard. I'd have to like angle it, and it'd have to happen like in the first centimeter or something like that, right? Okay, I've got yet another one. Somebody brought me this. And there seems to be like there'd be something I could do with it if I could only find my overhead projector. Where's my overhead projector? You'd think I'd have an overhead projector, wouldn't you? I don't have an overhead projector. I think somebody borrowed it. I know. I do have a projector, though. We'll try it with a big projector. I'll try it without like breaking my projector. This is kind of fun. This is a very large piece of plastic. Let's see what. They're like begging for a fight. Is that working?
Oh, I think so.
That's kind of fun, huh? Is that bright?
Maybe?
Yeah, I know. It's like at the dentist. Here, they shine a bright light. Yeah, it stays largely in here. Okay, so this is. Do you guys remember? Nobody remember. Anybody know Mitch Toller? Mitchell Toller. Went to the Air Force. He was taller than the rest